Homework question 11.8 asks us calculate the final temperature of the mixture, assuming that no heat is lost to the surroundings. So we see that we start at negative 14 degrees Celsius. We can assume that the final mixture will be water. So if that's the case, what has to happen to our ice is that it has to increase in temperature to 0 degrees. Once it increases to 0 degrees, which is its melting point, it has to have a phase change, which is represented by this flat line. It then has to increase in temperature while in the liquid phase to some unknown final temperature. Let's mark that right here. I'm going to call this one step 1, this one step 2, and this one step 3. We also have to consider our hot water. So our hot water started at 70 degrees Celsius, and then it had to end at the same temperature as our ice that gained energy. So it's losing energy to become cooler. I'm going to label this 4. So we're assuming that no heat is lost to the surroundings, which means that the heat gained by the ice will be equal to the heat lost, hence the negative sign, by the liquid water. All of these steps put together for the ice, so 1 plus 2 plus 3, all of this heat gain must equal the heat lost by the water. If we look at step 1, we see it's ice gaining energy from negative 14 degrees Celsius to 0 degrees Celsius. When we see a diagonal line like this, we have to use Q equals mc delta T. So our Q then is equal to the mass of our ice, which is 15 grams, multiplied by the specific heat of ice, so that's 2.08 joules per gram degree Celsius, multiplied by the change in temperature. We're going from negative 14 degrees Celsius to the melting point, 436.8 joules. The next step, step 2, is a phase change, and that's indicated by the fact that it's just a straight horizontal line. We know this phase change is from solid to liquid, so it's melting, and we have to use this value here, the heat of fusion, in order to determine how much energy is required for this phase change to occur. We see that this is a per mole value, so we start with the number of grams of our ice. We convert that to moles using the molar mass of water. We can then multiply that by the heat of fusion, and we see that that cancels out our moles, and we're left with kilojoules. We want to make sure that every number we use is going to be in the same unit. So we don't want to have joules for number 1, for instance, and then kilojoules for step 2. So I'm going to go ahead and convert this to joules just to be consistent. And we get a value of 4,994.45 joules for this step. Step 3 is another diagonal line, so we're going to use Q equals mc delta T, but here it gets a little tricky because we don't know what our TF is. So we're going to leave this in terms of variables, and we'll see that Q is equal to our original 15-gram sample times now the specific heat of water as a liquid because we underwent this phase change into the liquid phase, and then we're going to multiply it by the final temperature, which is right now an unknown, minus 0 degrees Celsius. If we do the algebra to multiply this out, we get 15 times 4.18, which is 62.7, multiplied by TF minus 0. So the 0 will cancel out, and we'll just have 62.7 TF. Now let's look at step 4. It's a diagonal, so it will be a Q equals mc delta T process. Again, we know our initial temperature for this system, but we don't know the final temperature, so we'll have to leave it in terms of variables again. Quick conversion I want to do before we jump into the math is to turn this 100 milliliters into a mass. If the density is 1 gram per milliliter, we find that we have 100 grams. Here we get that Q is equal to 100 grams times the specific heat of water as a liquid, since we started in the liquid phase, multiplied by the final temperature, our unknown, minus the initial temperature of the hot water, which was 70 degrees. And that gives us 418 TF, 29260. Step 1 plus step 2 plus step 3 was equal to negative step 4, so we can go ahead and write that in with our values. We can combine like terms on both sides. Isolate the TF, divide by 480.7, and we get that our final temperature is equal to 49.57 degrees Celsius.